So what we're looking at is we're looking at angle launching, but we're looking at a very specific type of problem. It's still angle launching. It's still with no elevation change, but we're looking at what happens if the initial velocity or the angle is not given. Okay, because the first step is find VOX, find VOY, but you need to know VO and you need to know the angle of launch. And so what happens if that's not given? Because there's tons of problems like that. What happens is without doing a lot of algebra or having the range equation, we can't solve them. And so the criteria for what I'm going to show you today is that it has to be an angle problem and there can't be an elevation change. Next class, we'll look at elevation change, true elevation change, not like the bell work problem that we just did. So when either the initial velocity of the angle is not given, right, that means we can't do step one. So we need a new approach. We need another equation to help us solve the problem. And so I'm going to show you how this is derived. You guys don't need to know how it's derived. This is the kind of stuff you do in college physics a lot. My AP physics class doesn't get this equation, right? They get a formula sheet that AP provides to them. So I've shown them the algebra to make this equation. Ultimately, they either memorize it or they have to derive it themselves. But you guys don't have to do that. But I want you to know where it comes from so you know when you can use it. Because it's not an equation that you can just use whenever you want to. It's for very specific conditions. So the conditions are, A, there can't be an elevation change, and it has to be an angle problem. And then you'll see that once you understand the equation, it's going to be kind of a shortcut to some of the problems that you guys just did for homework. And you'll see once I show you the equation. But it's a necessity if, and this is the key, what happens if one of these two guys is unknown? Right? Well, if that's the case, we can't do this right off the bat. Right? We can't find VOX and we can't find VOY because either this or this is not given, right? And so that puts everything to a halt, but we have an equation that will help us kind of backtrack, find that value, so then we can do what we learned last class. We kind of need a new approach or a new equation. So now this is where it comes from. Again, there's a bunch of algebra steps. You don't need to know the algebra steps. But I don't believe in just giving you an equation and saying, okay, here's an equation. I want you to know where it came from, so it maybe helps understand when you can use it. Right. So again, we know this is our first step. So, but we have to do it all in terms of letters, right? All in terms are variables because we don't have numbers right now. So we're deriving an equation. We know that the horizontal velocity is constant. It's called the range equation, right? So that means we're solving for dx because dx is the range. So that's why I started with the x equation, right? I solved it for dx equals vx times time. So now here's what we do is we want to substitute things in for this, and we want to substitute things in for that. The first thing we're going to substitute in is for Vx, we're going to substitute in VO cosine of theta, right? So I get rid of this and I put in how I would calculate it if I had the values, okay? So all I did was made one substitution. I took that and I plugged it in right there to get this. Now what I want to do is I want to figure out, well, how can I get rid of time? I want an equation that doesn't have time in it. So obviously, if I'm using the x equation here to get time, I'm going to need to use the y equation. So I start out with the y equation here. Again, remember, and this is the key, and this is why it only works for things that go like this, right? Because I'm making this equal to 0. So I take this equation, I make this equal to 0 here. Now we're solving this for time, right? And so this is what some of the math that we went over last class. So at this point, you either factor out a time, a t out of every term, or you divide everything by a t, however you'd like to do it. I think I showed you guys kind of both ways of doing this, right? But if I factor out a t and a t, it looks like this, and I can divide over by t, because we know the time is 0, this is 0 when time is 0 or when this value of t is true. So let me subtract over the v naught VOY, multiply by 2, right, and divide by g. Sorry, this should not be squared because it wasn't squared right there. Don't know why I did that. And so we get this result for time, right? Which you did, we did last class when we went over the couple problems. But VOY can be simplified farther, right? Because we know VOY is equal to VO sine of theta. So I'm going to get rid of VOY and put in VO sine of theta. And so it looks like this, right? If we get it down to the bare bones, this is how you solve for time. Initial velocity given, angle given, G given, right? That's how we did it last class. So again, remember from the previous slide that dx was equal to VO cosine of theta times the time. And so now what I'm doing is I'm substituting in this, right? Once we solve for time, I'm substituting that in right there for t, right? And so now I plug that in and I have this right here. Well, that looks messier than what we started with, right? So we want to clean this up a little bit so we can combine some things that are the same. There's a negative sign there, so I put it out front. There's an initial velocity and an initial velocity. Multiplying them, we get V naught squared. I have 2 cosine, sine. I have G on the bottom. Right now, the last thing we can do to simplify this is we can take that, and in your trig class, whether you're in trig now or you've taken it, you will have learned that this is one of those double angle identities. I don't know why you would want to have to memorize these things, but I'm assuming your math teachers make you memorize some of this stuff. That's the one nice thing about physics, is that we don't make you memorize things. You just have to know where to look them up, right? That's what engineers do. They don't memorize stuff. They look up the equations when they need to. So we can simplify that by putting this in, which helps clean it up a little bit, and we get this as our result. This is called the range equation. Now, it's been on your formula sheet. Some of you guys have used it before today when you really shouldn't have, because we didn't have a reason to use it yet. So we have the range equation. So you're going to see, I'm going to show you a couple problems where we need to use it to help us kind of get the ball rolling, so to speak, when we get a problem, if the initial velocity or the angle is not given. But as you can see, for some of the homework problems that you did, if you completed the homework, if you look at this equation, knowing that this is given and this is given and the problem's on Earth, if it asked if it asked you for the horizontal distance, well, you don't need to find VOX, you don't need to find VOA, you don't need to find time. You can just plug and chug and figure out where it's going to land based on just the initial velocity and the angle. So in that respect, it can be a shortcut to solving the horizontal distance. Now you're going to see for this, the two problems that we're going to do here, that we need to use it to find the initial velocity, and then after that, we're going to go back to what we did before to either find, in this case, time or the maximum height. And so this is a real problem. It was a textbook problem, and I kind of spiced it up a little bit by looking up some of the things, because I knew in Calaveras County they do I'm assuming at a fair or an annual event, they do a frog jumping competition. And this is some real, I was able to find real legit numbers here. Rosie the Riveter in 1986 jumped 6.5 meters. That's the world record for a frog. So think about 6.5 yards roughly, right? That's pretty far. I don't know how big the frog was. This is not Rosie. This was just a picture that goes with a problem. I was searching frogs jumping, and I found one because you can see he's doing an upside down parabola, right? He's doing the motion that we need. So Rosie jumps at 40 degrees. Had Rosie been a good physics student, Rosie would have known that 45 would make her go farther, right? 45 is the optimal angle, but we'll give her some slack because Rosie's a frog. We want to know what is the frog's initial velocity and then how much time was she in the air. And so, right, you look at this and you're like, all right, well, I don't know the initial velocity. So I can't find VOX, I can't find VOY, but I am given the horizontal distance. And so there's going to be a trade-off. If the initial velocity of the angle is not given, then the horizontal distance has to be given. We know that the vertical acceleration will equal g, and we know the angle is 40 degrees. And so this is going to be the clue when you're like, well, if I'm not given one of these values, then I probably have to use the range equation, right? That's going to help you figure out when using this is not just to make the problem a little easier, but a necessity. Because in this problem, right, we don't know the initial velocity. And to do anything, we need to know the initial velocity. And so we've got to find the initial velocity, and we're going to use the range equation to help us do that. So that means we're going to solve for VO, right, the initial velocity. So the first thing I'm going to do is I'm going to multiply both sides by a negative. And then I'm going to multiply both sides by g. Right, if I multiply both sides by g, that'll go over. And now I'm left with the initial velocity squared sine 2 theta. Now I'm going to divide both sides by sine 2 theta. So that cancels. Now I have the initial velocity squared equals, but we want the initial velocity. So I'm going to take the square root of both sides, and that will give me the initial velocity. So now I can plug in everything that I have, right? This was 6.5. Remember, g is negative 10, because we have a negative there, and somehow we need to be able to take the square root appropriately. Sine of 2 times 40 degrees. So some algebra that we haven't seen yet, but should be in your wheelhouse. Now, here's the one thing. When you're doing this part, right, I'll erase this in a minute. This is not the same thing as this. We don't want this. What we do is we do the sine of 80 on our calculator. So don't do the sine of 2 times the sine of 40, right? You multiply these two numbers together first, then you take the sine. Okay, that's what we're looking to do with that part of the equation. So 6.5 times 10 is obviously 65. Dividing that by the sine of 80, again, calculator in degrees, that gives me 66, and I take the square root of 66, and I get 8.124, right? But I'm just going to call it 8.1. So now I have the initial velocity. So now the problem might ask you for time. It might ask you for, right, what is this value? We already know this value, so it wouldn't ask for that again. So really the only choices are what is dy or what is time. So this one says time. So then again, you have your choice. Do you want to use the x equation to solve for time, or do you want to use the y equation to solve for time? I would use the x equation always, right? Whenever you can. Oops, sorry. It didn't like me. Right? If we can use this equation to solve for time, that's the way to go, because all you have to do is divide, right, the horizontal distance by the horizontal velocity. So now we need to find, right, the horizontal velocity. We found the initial velocity, but now we multiply that by the cosine of theta. And so we don't need to go through and find VOX and VOY. We just need to find VOX because that's what we're going to use right here, right? We don't need VOY because we're not using a y equation. And so now you can look at it and not just be solving things that you don't necessarily need. All right, 8.1 times cosine of 40, which is 6.2235, right? So I'm just going to call it 6.2. Right, and so now when I come over here to solve for time, I take the 6.5 that was given, and I divide it by the 6.2, and obviously that's going to come out to be like 1.04. So I would just call it 1 second, right? So to go from right here to right here, it takes the frog 1 second to make that jump. So we know it reaches its highest point at 0.5 if the problem asked us to go through and solve for that. But it doesn't, so it just wanted us to find time. But so the key is using this guy, the range equation, to find the initial velocity because we weren't given that to begin with. Once we're given that, now we can go back to doing the things that we did last class. But we don't need to do all the steps that we did. We just need to do the steps necessary, in this case, to find time. Any questions on that? All right, let me do one more here. And now this one's a little different, a little trickier because it asks for the angle. And so, again, it's just using trig functions, but we got to use it to find the angle. So Donald Duck is hitting the ball like this, right? It's 150 meters from there to there. So again, we're given this dx value, but this time we're given the initial speed that he hits the ball at is 40, but we don't know the angle. And then it wants us to find this, right? What is the highest point? What is dy in the middle? So again, when you look at the question, you're like, all right, what's given? Initial velocity. Angle, no. Dx, yes. That's when I want to use the range equation. So that's my starting point, right? I know I need to use this equation. I don't know how to make this not make these random lines. I can't write any softer. Maybe I need to write firmer. Maybe that's it. All right, so I want to start with the range equation, but now I need to solve for theta. Okay, now I know some of you that will cause some angst there. You'll get a little uptight about dealing with trig functions, but just pretend that this is together and keep it together and get the sine 2 theta all by itself first. So again, I'm going to multiply both sides by a negative. I'm going to multiply both sides by g. Right, so I get rid of the fraction, so to speak, or the denominator. Now I'm going to divide both sides by the initial velocity squared. So that cancels. So now I have sine 2 theta right? Sine 2 theta equals this. So if it was just sine theta, we would do the inverse sine to get theta. Well, we're going to do the same thing, but what we're left with is 2 theta on that side, right? So we do the inverse trig function. So you would take all these numbers and do the math, right? We don't have any numbers yet that we're going to plug in. Right? So we would do this math, inverse sine. Now, whenever you do this, If somehow you end up with a number greater than 1 here, then you made a math error because you can't do the inverse sine of a number greater than 1. It won't work. But we don't want 2 theta, we want theta. So we're just simply going to divide all of this by 2 in the end. And then that will give us the angle that we need. All right, so now I'm going to plug in my numbers. Dx was given as 150. G is -10. Right? VO is 40, and that's squared. So you have 1500, right? 150 times 10 is 1500. 40 squared is 1600. So that's 0.9375, right? So when you do what's in parentheses, I'm getting 0.9375 for all of this. So I need to do the inverse trig function of 0.9375. And that gives me 69.6 degrees. But that's divided by 2, right? Because 2 theta, we divided both sides by 2. All of this divided by 2 is 34.8. And that's the angle that he hit the ball at to make it go 150 meters at an angle of, or at a speed of 40 meters per second. So we found part A. Now it says at this angle, what would be the golf ball's maximum height? Right, and so now we want to know, what is this value from there to there? Now, do we know time? No. Is there a way to find the maximum height without knowing time? Yes. Let's use it then, right? So we want to use this equation because we don't know time, and we don't want to add more steps if we don't have to. And so when we use this equation to find the maximum height, what did we say this value was at its highest point? It's equal to 0. So we know at the highest point that Vy is equal to 0. And so we obviously could go through and solve for time, but I like to work smarter, not harder. I don't want to solve for things I don't have to solve for. And since we have this way of solving for dy based without time, and we know this value at its highest point is 0, then, right, that's an easier way to go. So when I do the math for this, right, and then divide by 2g, and the good thing is, besides that I showed it to you last class, we use this equation to find how high something goes in the previous unit a lot. So now when I look at this, what do I need to know? Well, I have G already, I know 2. I just need to find VOY, right? So in this problem, I don't need VOX, but I do need to know what VOY is. So I take the initial velocity, which was 40. And now this is why I needed that angle again. Right, 40 times sine of 34.8. Which is 22.8. Right, and that negative sign out there is because of subtraction, so it doesn't get squared. And it goes away because G is also negative. So I square the 22.8 and divide that by 20, and I get just over 26 meters tall for its maximum height. Questions on that? Okay. So I want you to click here on this. I've hyperlinked it so you can go right to this web page. It's at the CK12. I don't think they're going to make you sign up. And so and I'll click on it here in a second, but here's the sheet that I made that kind of has the directions. This is also hyperlinked right here. Here's a tutorial if you click on that. But it shows you, this is the page it'll go to, part of it anyway. There's two graphs, and I'll show you all of this before you go anyway. And then I made a little chart for you to kind of basically go through and get these values and then use the range equation for the 3 different target distances. You're not going to get through all 3 of them. But so just like it says here, this is just an activity in class to practice using the range equation. Gives you a chance to use some physics, not just in problem solving. So if you click on this, it will take you to this interactives.ck12.org. If you click on this, it kind of walks you through the whole simulation, but you can skip that by just going over here and you get right to the simulation. So there's not a lot of different things you can do here, but it lets you go from 12 to 10 to 8 in terms of the target. We're not doing elevation changes yet. And so it turns out that from where she has this arrow above the ground, this is 1.5 meters. And I know it doesn't look like it, but if you hit it dead center in the bullseye down to the ground, it's 1.5 meters. So if you get the perfect angle, then in the perfect initial velocity, there's not an elevation change. So you want to keep this on standing. If you start at 12 meters, so you know dx, what you have to do, and this is my suggestion, is pick an angle, right? And so maybe you make it 25. So use this angle, use this as dx, and solve using the range equation for what the launch speed should be. Now this, you see it only goes up by 1s. So maybe you use the range equation and it comes out to be like 12.8, and you're like, all right, well, I'll pick 13, and you hit go. Right, so you can see I was a little bit high. So maybe I'll try 12. And I'll probably be a little low, right? So I'm a little bit low. Now, when it asks for the vertical position, this is a position time graph, this is a velocity time graph. This color one is the horizontal, but this one is the vertical. If you just click on that white dot, you see it says 1.1, comma 1.4. That tells me that the 1.1 is the time, the 1.4 is the vertical distance. That means from here to here is 1.4. Right there is 1.5. So I'm 0.1 meters below. So obviously that's not optimal. Now, if I come over here though, I can change these 2 features by simply taking this white dot and moving it. This one's for the horizontal velocity, this one's for the vertical velocity. So right now the vertical velocity is 5.1. So if that was the one I wanted to use, I would put that in the chart. This is the horizontal velocity. Right now it's the 0.5 is time, the 10.9 is the horizontal velocity. Well, what I can do is I can move this, and you'll see that it changes the angles. It kind of fine tunes, right? So now I'm at 23.8 and 12.57. And so I might try that and see I'm a little bit closer. And that's at 1.5. And that's probably about as good as you're going to get. I mean, you could change this a little bit more to get maybe a little bit more in the middle, but it's pretty close to being dead center in the middle. So what I would do on my chart over here, right, launch speed. So I look at this. My launch speed was 12.57, so I'd write that down. Launch angle, I ended up with 23.8 degrees, right? Then it says horizontal speed, initial vertical speed. This is what I do is I come over here and I just click on that, and it's 4.9 for VY. Nope, I think I just changed this, but I click on that and it's 11.5 for VX, right? And then the other thing it asks for is the vertical position at the bullseye, so dy. That's what I showed you before, but it went away. So obviously it changed a little bit on me here. But if I click on that, right, it's 1.4. And then what you do, so then that's a good set of data. And so then use the range equation to see if you get that set of numbers to be 8 meters. And then try the 10 meters and try the 12 meters. Okay, so I know we don't have